Good morning, everyone. First of all, let me sincerely thank Jesus Aguiar for his kind invitation to deliver this plenary talk at the 25th International Conference, Computational and Mathematical Methods in Science and Engineering. It is truly an honor and a pleasure for me to share some of my recent research. The title of my presentation is Entropy-guided least square for robust smoothing of noisy data. Let me also acknowledge these two National Recovery and Resilience Plan projects. This work is the result of a collaboration with several colleagues. The team involved includes Pierluigi Amodio, Antonella Falini, and Francesca Mazzia from the University of Bari, as well as Luigi Brugnano from the University of Florence and Domenico Giordano from the European Space Agency. The main idea behind this research is to exploit the concept of entropy, widely used in statistical mechanics and information theory, to increase the robustness of model-fitting procedures. Here is an outline of my talk. I will begin by explaining the motivations behind this research and then briefly review the role of entropy in information theory and statistical mechanics. I will introduce the entropy-based methodology in a general setting and illustrate it using a specific test problem which we called the hidden polynomial problem. The second part of the talk will focus on various applications, from spline functions and smoothing splines to bivariate splines and real-world datasets, such as electrodermal activity signals, mammograms, and oil paintings. Finally, I will conclude with some remarks and possible future directions. Let's start with the motivations. Here we see a dataset labeled S1 consisting of 66 points aligned along the arc of a parabola described by this equation. However, the data have been corrupted by Gaussian noise with zero mean and a variance of 9. When we apply an ordinary least squares approximation using a smoothing spline with penalty parameter selected via leave one out cross-validation, everything works fine and we recover the right pattern. It is the blue solid line in the picture. Now we add a second dataset called S2 consisting of 34 points represented as black dots surrounded by circles in the plot. The subset S2 forms a random cloud of points confined above the left part of the arc of parabola. These points deviate significantly from the parabola and can be regarded as outliers. In real-world scenarios, such outliers often arise due to poor sampling, measurement errors, or data processing issues. These uncertainties can compromise the reliability of ordinary least square approximation, leading to misleading conclusions, and, in fact, the ordinary least squares approximation here fails to recover the true underlying pattern. The approximation is overly influenced by the noise. To address these challenges, we turn to the concept of entropy in information theory introduced by Claude Shannon in 1948. Imagine a collection of possible events each with an associated probability of occurrence denoted as P1, P2 up to Pn. Then a natural question arises. Can we quantify the level of uncertainty about which outcome will actually occur? Let's denote such a measure by capital H. Shannon proposed that capital H should satisfy a few intuitive properties. First of all, continuity. H should vary continuously with its arguments. Secondly, monotonicity, which in simple terms means that having more equally likely possibilities makes the situation more uncertain. And finally, consistency. If we split the probability space into parts and compute the uncertainty in stages, then the total measure of uncertainty should remain unchanged. For example, consider a situation where we first choose between two options, each with probability 1/2, and if the second option occurs, we then choose between two further possibilities with probabilities 2/3 and 1/3. Then the overall uncertainty should be consistent whether we consider this as a single decision or a sequence of two decisions. Shannon showed that up to a positive scaling constant, the only function h satisfying these three assumptions is defined as minus the sum of probabilities times their logarithm. This formula, known today as Shannon's entropy, has become a cornerstone of information theory. Building on Shannon's idea, Edwin James proposed his principle of maximum entropy. When we have no prior knowledge about a set of outcomes, we assign equal probabilities to each. This is the principle of indifference rooted in Laplace's work. But what if we gain some information suggesting outcomes are no longer equally likely? We need some different criterion to assign probabilities. James' principle of maximum entropy tells us how to proceed. We should pick the distribution that maximizes entropy, subject to the constraint imposed by our new knowledge. In James' words, the distribution that maximizes h, subject to the constraints which represent whatever information we have, provides the most honest description of what we know. This approach systematically updates probabilities, preserving objectivity and minimizing bias. This principle plays a crucial role in our approach, and I will introduce it in a general setting, meaning that the model is not necessarily linear and the cost function is not necessarily the mean squared error. So we are given a dataset consisting of m points, a proper model to fit the data, which is denoted by f and depends upon s coefficients, s parameters, denoted by C1, C2, Cs, which should be trained during the fitting procedure. And finally, a cost function capital C, which may be regarded as a weighted mean over cost over contribution capital Ci coming from each individual training point Yi. So the weights are positive and sum to 1. Due to this normalization condition, we can interpret the weight distribution Wi as a probability distribution, and so we can compute the associated entropy. So this quantity must be regarded as the expected value of the information content, or uncertainty. So we introduce the following mathematical problem. Using the principle of maximum entropy of Jaynes, we want to solve this constraint problem, maximize the entropy subject to two constraints. The first one is, of course, the normalization condition, and the second one is consisting in imposing a prescribed given value to the cost function capital C. Okay, we will see in a while what's the difference between the standard approach, the ordinary least square approach, and this new approach. In this talk, I will consider datasets consisting of time series defined on the real line in the plane and three-dimensional space, or datasets representing an image or a point cloud. Concerning the model, we will confine only on linear models, and in detail, f will be a polynomial, a univariate or bivariate spline function, spline curve or surface, or finally a smoothing spline of degree 3. Concerning cost function, we will only consider the weighted mean square error, or for smoothing spline, the penalized weighted mean square error, where we see this additional term where lambda is the smoothing parameter. In this slide, we highlight the differences between ordinary least squares and our new approach, which is called maximal entropy weighted least squares. In ordinary least squares, we minimize the mean squared error for a given set of weights. Typically, these are uniform weights. Here, the mean square error is, of course, an output parameter. In our maximal entropy weighted least squares, we reverse the perspective. We fix the desired mean square error as an input parameter and let entropy maximization guide the selection of optimal weights and model parameters. This leads to a nonlinear system but offers far greater robustness. To illustrate the entropy-based methodology, we consider this synthetic dataset consisting of 100 points. We start with 25 points lying exactly on a Legendre polynomial of degree 7, which is shifted in the interval 0, 1. Then we add 75 corrupted randomly chosen points. The ordinary least square approximation, shown here as the blue solid line, performs poorly due to the overwhelming influence of the noisy data. Now, we progressively reduce the prescribed mean squared error and apply our maximum entropy weighted least squares technique. For example, in this picture, we have halved the original value of the mean square error corresponding to uniform weights, and we have obtained the results highlighted as the solid red line in the picture. If we continue For example, we choose a scaling factor of 1 over 5, then a scaling factor of 1 over 10 and 1 over 20, we see that the fit converges toward the true polynomial, and at the same time the entropy decreases, which means that the weight distribution is progressively departing from the initial uniform configuration. Let us continue. Here is the configuration corresponding to a scaling factor of 1 over 50, 1 over 100, and finally 1 over 1 million. In this final configuration, the red line is superimposed to the green exact configuration of the Lagrange polynomial. This means that all outliers have been detected and successfully removed. Mathematically, the problem is formulated by constructing a Lagrangian function that includes the entropy term, the normalization condition, and the fixed mean square error constraints. Here, alpha and beta are the two Lagrangian multipliers. Then we compute the stationary points by computing the gradient of the Lagrangian function and obtain a nonlinear system. Here, one scalar equation, the third one, and one multiplier, namely alpha, may be removed, and one arrive at the following set of equations. In case the model is linear, this is our case, we see that the equations in A identify the so-called normal system, which is indeed a linear equation to be solved, in the unknown C, where C is the set of the parameters of the coefficients inside the model. So this suggests the following iterative procedure to compute the solution of this system. We initially start from initial weight distribution, typically the uniform weight distribution, and we set the desired minimal mean squared error. Then we evaluate the coefficient Ci from A by solving the normal linear system. Then we update the Lagrangian multiplier beta from the second scalar equation, which is nonlinear in beta. And finally, we update the weights Wk, which are explicitly defined by equation in C. Okay. Then we repeat from step 2 until convergence is attained. Now let us consider a few illustrative examples. As first example, we consider a dataset consisting of 44 points. Out of these, 32 points closely follow a given profile, while the remaining 12 consistently deviate from it. To approximate the data, we use a spline of degree 2 defined on a regular and uniform knot sequence composed of 20 nodes covering the interval from 0 to 1. In this plot, we see the result of applying ordinary least squares. The blue line represents the spline approximation using uniform weights. It is clear that the 12 anomalous points, our outliers, have a strong influence on the result. The fit is visibly distorted. To improve this, we reduce the mean square error and apply the maximal entropy principle to guide the selection of weights. Here, the blue line again shows the ordinal least square approximation. The red line is the result of applying the maximum entropy weighted least square. Notice how it is much closer to the underlying profile, largely ignoring the influence of the outliers. The red circles mark the outlier as identified by the algorithm. In fact, they correspond to points with weights approaching 0. Finally, in this plot, we see the maximal entropy approximation again in red and the outliers identified by the strategy as red circles. For comparison, the green dashed line shows the ordinal least squares approximation obtained after manually removing these outliers from the dataset. This demonstrates that the approach based on entropy, on the maximization of entropy, effectively detects and neutralizes outliers automatically without requiring prior knowledge about their presence. Let us return to the example I presented earlier when discussing the motivations. Recall that S1 consists of the black dots distributed along the arc of a parabola, while S2, represented by the dots surrounded by circles, forms a cloud of outliers that significantly depart from this quadratic pattern. The table here summarizes the mean squared error values obtained with uniform weights, using ordinary least squares. It shows the results of applying a classical smoothing spline to both the clean dataset S1 and the contaminated dataset formed by the union of S1 and S2. The smoothing parameter lambda was determined through leave-one-out cross-validation. We can immediately see that the mean square error for the entire dataset S1 plus S2 is more than one order greater, clearly reflecting the impact of the outliers. Now, suppose that we already know from previous experiments or from the literature an estimate of the mean square error corresponding to a clean, outlier-free dataset. Later, I'll show you a real-world case where such a reference value is actually available. This reference can then be used as the target mean square error in our optimization problem. In this situation, this is the desired value of the mean square error. So, we consider this constraint optimization problem, and the input mean square error was given by previous experiment or by the literature. By solving this, we obtain the red line shown in the picture, which represents the maximal entropy least square approximation. Notice how this solution effectively ignores the influence of the outliers, recovering the underlying trend. Here, the working assumption is that the expected value of the mean square error is already determined within the context. But what happens if we lack any prior information about outliers in the dataset? In this case, estimating an approximate mean square error beforehand is not feasible. To address this, we adopt a continuation technique combined with robust statistics to detect potential outliers. In particular, the method works by progressively reducing the mean square error from its initial value with uniform weights. At each step, we monitor the residuals EI, defined as the difference between the ordinates yi and y hat I, which is the value predicted by our model. We compute their median bar E and the median absolute deviation, which is defined here, and we use the criterion based on the median absolute deviation and described here to detect outlier. An outlier is a point whose residual escapes from this interval, which is centered in bar E. Here, the constant kappa is approximately 1.48 and is a scaling factor that makes the median absolute deviation, to be a consistent estimator of the standard deviation. As the mean square error decreases, points with large residuals get assigned smaller weights and their influence fades. These residuals eventually escape the cutoff interval, leading to their detection as outliers. The figure here illustrates this process. The blue line shows the residual median bar E, while the red lines define the cutoff interval, which narrows as the mean square error is decreased. So the picture must be interpreted from right to left. Once the cutoff interval reaches a plateau, no further points leave it, indicating that all remaining data are inliers. So the appropriate mean square error reduction is determined near this plateau. For example, it is in this picture around 6 times 10 to the minus 2 of initial mean square error. Finally, this approach is capable of splitting the original dataset in two subsets, namely inliers and outliers, and in this picture these outliers are detected by this procedure and highlighted by black dots surrounded by green squares. But this approach also provides a score for each outlier, ranking them by the mean square error reduction level at which they are detected. For example, the point 68 in the dataset has a score of 1. It is identified as an outlier even with uniform weights, while the point 50 in the dataset is the last significant and is detected as outlier only at a much lower mean square error, and so it receives a score of about 6.5 times 10 to the minus 2. So we can construct this bar diagram displaying the scores of all detected outliers and introduce an order in the outlier set according to their importance, their influence on the final shape of the model. Well, two fast examples follow now. The first one is, in both cases we have two spline curves, one in the plane, in this one we define 200 points on the arithmetic spiral, whose parametric equation is this one, and introduce perturbation on 100 of them. And you can see here in the picture the blue solid line representing the ordinary least square approximation, while the red solid line represents the maximal entropy least square approximation. A similar results in reproducing an helix in the three-dimensional space. We start with 500 points on the helix described by this parametric equation, and introduce random noise in half of them. Again, the blue line is least square approximation, the red line, which is a little bit hidden inside the black dots corresponding to the helix. Well, the red line is the maximal entropy least square approximation. The next example involves a spline surface. We consider Franke's function a widely used test function in interpolation problems. It is characterized by two Gaussian peaks of different heights and a smaller dip, which makes it a challenging and interesting surface to reconstruct from scattered data. This function was originally introduced by Franke in 1979 for comparing different interpolation methods. In our experiment, we randomly sampled 1000 points from Franke's function and perturbed their values by adding Gaussian noise with zero mean and variance of 10 to the minus 3. To reconstruct the surface, we used a cubic B-spline defined on a grid of sides 10 times 10. The knots were carefully chosen to ensure interpolation at the four corners of the domain. As shown here in the picture, in absence of an outlier, the reconstruction performs very well and closely matches the true surface. Now, to make the problem more challenging, we introduce 150 additional points shown in red in the picture, sampled randomly from a uniform distribution. These points act as outlier because they clearly deviate from the smooth structure of Franke's function. As we can see, the ordinary least squares approximation struggles in this situation. The surface reconstruction is now heavily distorted by the anomalous data, failing to recover the original shape. Now, let's apply the maximal entropy weighted least square approach. By setting the target mean square error to be 100 times smaller than the value obtained with uniform weights, we see that the influence of outlier is effectively suppressed. The outlier points are assigned negligible weights, allowing the reconstruction to focus only on the genuine original data. As a result, the original surface shape of Franke's function is successfully restored, demonstrating the robustness of the maximum entropy methods. In this last illustrative example, we start with a structured dataset composed of 142 points, which are arranged on the surface of a sphere with radius 1. Here is how the experiment has been prepared. We trace level curves, that is circles on the sphere, introduce a number of points on each circle and perturb half of them. Again, our goal is to recover the original spherical surface by constructing a closed and regular cubic B-spline surface. The next picture shows the results of applying ordinary least squares to this dataset. You can see that the influence of the perturbed points is evident here. The reconstructed surface is visibly distorted and fails to preserve the original spherical shape. To address this, we apply the maximum entropy-weighted least square approach in an iterative process. Starting with this uniform weight distribution, we progressively reduce the mean square error and compute the maximum entropy-weighted least square approximation. The scaling factor we use are the following: 2, 3, 4, 5, 10, 20, 30, 40, 50, 100, 500, and 1000. And you can see that as the mean square error is progressively decreased, points whose contribution to the surface definition becomes negligible because they are assigned very small weights are detected as outliers. These points are marked by white circles in the visualization. As a result, the spherical surface is successfully recovered, demonstrating the effectiveness of the maximum entropy-weighted least square methods in handling even large perturbations in the data. In each example, we have considered up to now whether we are fitting spline functions, smoothing splines, or bivariate splines. The maximum entropy weighted least square approximation closely follow the underlying pattern, while automatically detecting outlier as points with weights approaching 0. In contrast, the ordinary least square approximation is clearly distorted by anomalous data. Now, let us see our method in action when applied to real-world problems. The first application concerns the identification of peaks within a signal representing electrodermal activity data of an individual. These two pictures show time series collected by means of a wristband that measures the conductance of epidermis in microsiemens. The location and amplitude of these peaks are correlated with the release of cortisol hormone, and therefore these peaks identify stressful emotional activities. In particular, the top picture refers to a baseline signal which has been obtained through a 6-minute relaxation session, and therefore this is assumed to be free of significant peaks, indicating a lack of stress. In contrast, the time series in the bottom picture has been collected from the same individual during daily activities in this range of time. The vertical dashed red line are the peaks detected by the MIT algorithm which come with the device. So we have tried to to detect peaks by means of the maximum entropy least square approach, and here is the result. We have used a smoothing spline. We have first used a smoothing spline approximation with uniform weight applied to the baseline signal, and we have obtained this value for the mean square error with uniform weights. So this is our reference value in absence of significant peaks. In contrast, we have solved the same problem but using the second time series, and we have obtained a mean square error whose value is more than one order greater than the previous value. So we have used the previous value as input value in our maximum entropy least square approximation, and we have detected outlier. These outliers are actually the peaks that you can see in this bottom picture. This recall that our approach can also assign a score to the importance of the outlier, and so you can see colors here, red, blue and green, indicating stress severity levels in decreasing order. So we have in our opinion much significant information with respect to the one given by the MIT algorithm. In the next example, we have applied the maximum entropy weighted least square approach as a computer-aided diagnosis tool to assist radiologists in identifying regions of interest in mammograms. The image shown here displays a mammogram of a breast with a dense mass located in the central region. This mass, which is indeed a malignant tumor, has an irregular and blurry boundary, which makes its detection and classification challenging. To achieve this, we solved the optimization problem using a cubic B-spline surface defined on a grid of sides 6 × 6, covering a rectangular area that embraces most of the breast tissue. Starting from the original mean square error corresponding to uniform weights, as usual, we reduced its value by a factor of 5. This yielded the weight distribution shown here, where lighter shades correspond to higher weights and darker shades indicate smaller weights. As we can see, the maximum entropy weighted least squares technique assigns very small weights to pixels inside the dense mass. From this weight distribution, we can extract level sets corresponding to the most significant intensity variations. These are the red contour lines superimposed on the original mammograph, which define the boundaries of potential region of interests. To further investigate the nature of the mass, we perform a fractal analysis of its boundary. In a study by Rangayan and Nguyen, the fractal dimension was proposed as a diagnostic feature to distinguish between malignant and benign breast masses. Their analysis showed that malignant tumors tend to have irregular, speculated boundaries with higher fractal dimensions, while benign masses exhibit smoother contours and lower fractal dimensions. Here we have extracted a binary representation of the weight distribution, labeling pixel corresponding to mass as 1 and background pixel as 0. Then we have used the MATLAB function hausdim to compute the Hausdorff fractal dimension, and we have obtained a value of 1.59 for the boundary of this mass. This high value supports the suspicion of malignancy, which in this case is indeed confirmed. Well, the last application consists in removing craquelure from an oil painting. What is craquelure? Craquelure is a fine network of cracks that naturally appears on surfaces of oil paintings over time, and it is particularly common in works painted on wooden panels, as we see in this example showing a close-up of Mona Lisa's eyes. These cracks form due to the aging of materials and the effect of environmental factors such as temperature and humidity changes. In particular, in oil painting of wooden supports, craquelure often results from the different rates of expansion and contraction between the paint, the varnish, and the wood. This is because this material responds differently to environment fluctuations, causing stress that leads to cracking. Anyway, the problem here is to detect and reduce the visual impact of these cracks while minimizing pixel level interventions. This is critical to preserving the original aesthetic qualitative of the artwork. So, our approach employs a bivariate spline model together with the maximal entropy weighted least square strategy. We first use this strategy to detect most of the pixels that form the crack pattern, and then for these identified pixels we replace their original red, green, blue values with those predicted by the spline model, thus filling in the cracks in a way that preserves surrounding textures and colors. Using our method, we identified approximately 14,000 pixels as outlier, and in fact these correspond to the cracks in the painting. This bottom image shows the detected outliers in white, highlighting the regions where our approach has assigned very small weights due to their deviation from the expected smooth surface. Finally, the restored image is displayed in the button here. Only about less than 14% of the total pixels were replaced, ensuring minimal intervention and thus preserving the integrity of the original artwork. To conclude, the maximum entropy weighted least squares approach offers a robust alternative to traditional least square methods, particularly in the presence of noise and outliers. Future directions include extending this approach to nonlinear models, or for example considering different kind of cost functions, as well as exploring application in machine learning and deep learning frameworks, and investigating stochastic differential equations under non-Gaussian noise. Thank you for your attention. I hope this talk has provided useful insights into the potential of entropy-based methods for robust data smoothing and their application across diverse fields. Goodbye.